Hello everyone. Uh, Welcome to chapter 5 network modeling. In this chapter we are talking about the network modeling, which is one of the most important problems that we see in our world. For example, the supply chain, you can model it as a network. Basically, in the network modeling, uh, each agent, each center is gonna work as a node, and the channel of the connection between the different nodes are modeled as a decision variables that you're going to see in the next coming slides. This network modeling is very useful. We are going to see a lot of the application of this modeling. This you already seen the network in the transshipment problem, the example of the network modeling, but in this chapter we are going to talk more about the network modeling, and you can find a lot of application of this type of problem in the reality. So let's start. Uh, the in this chapter we focus on the several important problems, transshipment problems, shortest path problems. The transshipment problem is the type of problem that we have several sources and we want to send out the material to different destinations. And when in this type of the problem, uh, we want to minimize the cost associated with this transshipment. And the shortest path problem is that we want to find, for example, we want to move station 1 to a station B, like in the city, and we are trying to find the shortest path that we can take. For example, like the ambulance, because the time is very important for this kind of the service. We can model a CD as a network. Each intersection is going to work as a node, and each CD is a road that connects different nodes. So we can model a CD as a network, and we are trying to find the shortest path, which is going to be in this case from hospital to the patient's house, and the reverse path, which is taking back the patient to the hospital. So you can grasp the concept that this is very important and practical. And then we have other type of the problem, like the transportation and assignment problem and the generalized network problem that you're going to see in this lecture. So let's start by the network law problem. This type of the problems, they have specific characters. In these cases, we have several agents like the suppliers or the destination source or the inventory houses that they are represented by a circle, and we call them nodes. Nodes are basically either they receive materials or they send out the materials. So we specify them into two main categories. Also, there is third categories that they get materials and send out the materials. So they can receive material from supply nodes and they can send to another type of the nodes. So basically, transshipment nodes are the nodes that they get the material and send out to some other nodes. We usually define the net demand of the each node. So we don't care how many transshipment they have done, but we mostly care about the final nodes. So final demand of each nodes. Usually we use represented by the negative numbers in the nodes. It means that they are suppliers. They can send out this much material to other nodes, and the positive means that they are demanding. They want to receive this kind of the materials from other nodes. Transshipments is in middle. That means they can work as a supplier and the demanding nodes, but remember that they have a final and net value that either is positive or negative. They cannot be both negative and a positive number at the same time. And then this is a example that we have. Suppose this is an example which is about a specific company. We have several nodes, New York, which has been labeled as a 1, and Boston as a 2nd. Each of these circles represent a node, and most of the time we represent these nodes by numbers, so we label them from 1 to the number of the nodes we have. We divided the nodes into 3 categories: suppliers, demanding, and transshipment. The suppliers, they have a negative values. That means they can send up to this value to the other nodes. And for example, node number 7 also is a supplier here, as well as the number 1. And then we have demanding nodes. Demanding nodes, they have a positive value next to them. So you can see node number 6 and node number 3 are positive, as well as the other nodes that you can see they are positive. And then the transshipments nodes are the one that they are in middle, so they can get material from other nodes and pass through other nodes. So right now, number 2 node number 2 gets material from node 1 and passes through number 3. And then we have some channels that connect different nodes to each other. We call them arc. For example, between node 1 and 2 we have an arc. Between 2 and 3 we have arc. And then you can see that between 5 and 3 we have 2 arcs. One is from 3 to 5 and another one is from 5 to 3. Basically it means that the number of the materials that can be transferred from station 3 to 5 costs $35, these values, and then from 5 to 3 that means they can cost $40. In terms of the modeling, each of these arcs represent one decision variable. So the number of the decision variables in the network is the number of the arcs that we have. And remember that the sign of the arcs, the direction of the arcs is very important. Most of the time in this chapter we are working on the all of the arcs, they are directed. That means there is a direction. You see, for example, this node 3 and 5, they have 2 arcs. One is toward 3. The direction is from 5 to 3, and one is from 3 to 5. So we call this directed graph, directed networks. That means the sign of the network is important. So as I just told you, we have cost of associated with each arc, and we want to minimize the cost of the this transportation problem. And the number of the parameters is equal to the number of the arcs that we have in the system. There is one more two type of the constraints. First of all, that we have to satisfy all the requirement, and then for example, this station node number 1 can send up to this materials, but there is one small hint that we have to consider. Uh, in the equation we have to write so let's first talk about the decision variables. The decision variables that we have is the number of the arcs that we can have. So basically we have xij is the number that shipped from station from node I to node j. So for example, we have x12 is the number of the cars that shipped from node 1 to node 2, and then from node 2 to node 3, and so on. So basically this is the decision variables that we have. And as this is a very important that we remember the number of the variables that we have is equal to the number of the arcs that we have in this system. Basically, the objective function is going to be the number of the materials that has been shipped from node 1 to node 2, which we represented by x12, and the cost associated with this shipment. So $30 is the cost of this shipment, and the number of the materials that shipped from 1 to 2 is the x12. And we add all the numbers. Remember, for station 3 and 5, we have to consider both ways of the shipments. That is, we have to consider x1 to x3 to x5 and x5 to x3. As you can see, right now $35 is moving from station 3 to 5, and $40 is associated with moving from 5 to 3. And this is the objective function, and then we have to define the cost. Basically, in the network flow problems, we have three situations. Total supplies is greater than total demand. The total supply means then all the summation of all the negative numbers that we have in the supplies. We have to consider the abstract value in terms of the positive value. So we convert the negative values to positive value and add all of them. And then the total demands. The total demands is the summation of all the positive numbers in the graph. If total supply is more than total demand, we write this problem as an inflow minus outflow greater than the supply or demand of each node. Inflow and outflow I'm gonna explain in a moment, but we if the total demand is greater than total supply, we have to write inflow minus outflow. So the first column is that this talks about the whole problem itself, but this talks about each node level. So first we have to talk about the total. We have to find out whether total supply is greater than total demand. If so, then at each level of the node, at each node we have to have this kind of the constraint. So the sign of the equality sign of the constraint depends on the whole program, whole problem itself. If, for example, if the total supply is equal to total demand, then we have to write inflow minus outflow equal to supply or demand of each node. So in our problem, we had two supplier nodes that had 200 and 300. So if we add them up, we get 500. So the total supply that we have is 500. Now let's look at the number of the demands. So the demands we have is 100 plus 60 plus 80 plus 70 plus 170. So if we add all of these numbers, we get the total demand is 480. So the total supply is greater than total demand. So we are in this category. Total supply is more than total demand. So in each level of the nodes, we have to define inflow minus outflow is greater or equal the supply and demand. So let's talk about inflow and outflow. Remember back to the picture that we have. Whatever comes to the node, we call them inflow. So right now for station number 2, X12 is inflow, and outflow is the material that goes out from the node. For example, for station number 2, X23 is the one that goes out from this node. But let's talk about the node 5, which has several outflow and inflow. The outflows are X53, X54 and X56. Basically X5J are the outflow of this station, and then we have inflow. The inflow are X35, X65 and X75. So Xi5 are the inflow of this one. So basically, because the total demand, total supply is more than total supply, we have to write equations at each node level, inflow minus outflow greater than supply demand. That means that for each station, for each node, we have to consider this equation. So for example, for station 1, for node 1, we don't have any inflow, so the inflow is 0 because no station is sending material to this one, so this is 0, minus the outflow. The outflow is the summation of x1, x2 and x1, x4. So 0 minus x1 2 minus x1 4 should be greater than the demand or supply, that in this case greater than minus 200. So the equation becomes x1 minus x1 2 minus x1 4 greater than minus 200. Now if you multiply this equation by minus 1, you are going to get x1 plus x2 less than 200. So basically means that this station can send up to 200 to station 2 and 4, which makes sense, right? Because this station has up to 200 materials, it has 200 materials, and then it can send up to 200 to station 2 and 4. So let's talk about one more node. Let's say talk about node 2. In node 2, the inflow is x12 and outflow is x23. So x12 minus x23 should be greater than equal to 100. That's it. That's we have here. Let's talk about node 5, that is a little complex and it has several nodes. As we just talked, the inflow is x35, x65 and x75. So if we add them up, and then the outflow is x53, x54 and x56, and add them up and subtract from the inflow, and the summation of this equation should be more than 170, which is the demand of this station. Also, so for each node we write the constraint. Remember that the number of the variables in the node network problem is equal to number of the arcs that we have, and the number of the constraint is exactly equal to number of the nodes that we have, as you see in the constraint. And then we have one more set of the constraint, which is non-negative conditions. That means all of the xij should be positive. We cannot send out negative material because it doesn't make sense, right? Okay, so let's model this problem in the Excel solver. The effective way to solve to model this problem in the Excel is that you write arcs way. That means you write the arcs that we have, or decision variables that we have. First start by the lowest number, in this case 1, and then in the two side write the available nodes that we have. For example, we have a node x12, that means it's going to from station 1 to station 2, and then from node 1 to node 4, and then from node 2 to node 3, and from node 3 to node 5, and so on. So for each node write the available arcs, and then that makes the decision variables that we have. And for each arc write the unit cost that you have. So from 1 to 2 is the cost associated with this transportation is $30, and from 2 to 3 and from 1 to 4 is $40, and so on. So you can write it. And then these columns define the decision variables, and this column is a coefficient of the objective function. So just we need to write the objective function. So we can use the sum product, which is a defined equation in the Excel. So decision variables are located in the B6 to B16. We select them and then we multiply by coefficient function. So this is our objective function. And the next one is that the net outflow of each of these nodes should be greater than of the supply or demand. So we have to compute the net flow of each node, because we don't have any, for the node 1 we don't have any outflow, we don't have any inflow, because in this column we don't have any 1, then the inflow of the node 1 is 0, but we have outflow. So we can write 0 minus x1, this value minus this value, and so on. But let's consider about the node 5, which is a complex one. So inflow of the node 5 is that we have 1 here and 1 here and 1 here. So we have 3 inflow for this constraint, for this node. As well, we have 3 outflow. So if you want to add them, there is a higher chance that we may forget some of the constraints, some of the coefficients, some of the decision variables that in the constraints, and we may have a wrong or incomplete constraint. There is a function that we can use for this purpose. So the function that we can use is called SUMIF, which is a built function in the Excel. The SUMIF function has 3 components: the range, and the range that we want to compare the criteria, and the criteria itself, and the range of the numbers that we want to add them up. So it has 3 components, and the function name is SUMIF. So because for each node we have to compute the inflow, we can use this sum if function. So the sum if function for this one is going to be, so we are uh, adding all these values, all these decision variables, and we are looking for inflow that they are coming to station node 1. So we can select station node 1, and they have to come to this station. We have to select this column. So this becomes the function that basically this function means that compare these values that they are in E6 to E16 to I6, that 1, and if these values are true, if this condition, if I6 is 1 is equal to one of these conditions, sum the cells that they have these values. So this is inflow. And then there is in the Excel we can log some of the cells because the sum range that we are talking is constant for all of the nodes. We can log these cells by pressing F4. You can log all the cells. So this means that we are logging, we are just adding all this range B6 to B16 are added, and then we can log on this one. So these values are fixed, and then I can drag down all these values. So you can see that for all of the constraints, just this value of the node has changed. The rest is remain constant. Now let's compute the outflow. So similarly, I use a sum if function, and the range that I want to add is the decision variables that they are sitting under this column, and I can lock them. So I just press F4 and all of them are locked. And then I'm comparing to outflow. So that means they are coming out this from specific cells, and so I have to compare this value to the range of the nodes that I have. So, and then I can lock these cells. So this basically sum if gives that compute the values that the value of the I6 matches with the value of this column. So let's test the example. Let's put 10 for the new arc. That means I'm sending 10 cars from station 1 to node 4. That means the outflow of the station 1 should be 10, and inflow of the station 4 should be 1. It should be 10. So you can test that we have exact 10 for both of the station that we just took. And then the net flow is going to be the difference between the inflow minus outflow that we have. So let's solve this problem using the solver. So our objective function is here, and we try to minimize it, and the set of the decision variables that we have is this decision variables, and then the set of the constraint that we have is net flow should be greater than or equal the demand or supply that we have, and that's all. And then we make sure that the decision variables are non-negative, and the type of the solver that we are using is a simplex linear program, and we can solve this problem. So this is the answer for the problem. You can see each of the values are appeared, and all of them are shown in the table. So basically this means that we are sending out 200 from station 1, which has the maximum possible that we could send, but the station 7, which is the supply station, we are keeping 200, and we are keeping 20 of them, and we are not supplying. And then you can see the other values for the uh, in this column. You can see the details. For example, as we just said, station 7 sends 280, which 210 of them is from station 2 goes to station number 5, and 70 of them goes to station 6, and the total cost associated with this shipment is $2,235. So this is basically solving a model using the solver for the transshipment problem. So if we look at the graphical way, you can see that node 1 is sending 80 and 120 to station 4 and 5, and station 4 is not sending anything out. But Atlanta, the node 5 is receiving 210 from station 7, and it sends out 40 to station 3, and station 2, node 2 is receiving 120 from station node 1 and sending out 20 of them to the node 3. So node 3 is receiving 40 from station node 5 and 20 from node 2. So this is the meaning of the solution that we got from the solver. Now let's talk about the shortest path problem. In this way, in this problem, we have a set of the nodes and possible arcs that they are connected through arcs, and we want to find the shortest path between two nodes. The practical example of this problem is the emergency vehicles, that like the ambulances. For example, the hospital got a call from a patient, so we are trying to find the shortest path from hospital to the patient's house. So you can see this is a very practical problem. This is a special case of the transshipment problem that we already solved. This problem is a special case of the transshipment problem that we had already in the previous problem. In this case, we have just only one supply and one demand node. The supply demand node has a supply of -1, and the demand node of that we have has a value of the +1, and the rest of the nodes are the value of the nodes are 0. And you can see that the number of the total supplies is equal to total number of the demands. That means all of the equations that we are going to have in this problem is equality. So let's look at the example. Here we want to move from station 1, which is a supply, and it has been represented by node number 1, and the supply of it is -1. We want to move to node 11, and it's the demand for this one is a positive one. This is basically like using a GPS. Your destination is given by 11, node 11, and your current position is station number 1. So you want to move from station 1 to station 11, and you want to use a GPS. The distance between possible points, possible nodes, or possible intersection is given by the number of hours as well as the quality of the road. Here we don't care about the quality of the road right now, because we just want to make our travel shortest as possible. So using the similar notation that we used for the previous problem, the number of arcs then defines the number of the variables that we have, and the number of the nodes defines the number of the constraints we have. And remember that for all of the middle points, transshipment nodes, the demand is 0, and so the number of inflows minus outflows should be equal to 0. So let's model this problem. So the objective problems that we can have, we just can have multiply hours multiplied by decision variables. That means 3 hours multiplied by x1 3 plus 2.5 hours multiply x1 2, and so on. So we add up all these arcs and their associated cost. So similar to the previous problem, we can have set up decision variables in this way. So this means that whether this is a decision variables that we have, and this is from to destination that we have. There is one slight difference between this problem and another problem, the problem that we discussed in the transshipment, but for time being, let's ignore that. So basically we are setting the problem as we did for the transshipment problem, and then we compute the net flow. The net flow is the difference of the inflow minus outflow is equal to the demand. The destination has the destination with a node number 11 has a demand of 1, and the destination for the source that we want to move on we want to start our journey is node number 1, and it has a -1 supply. So the net flow should be equal to these values, and the objective function is the driving times multiplied by the driving times and the routes that we are selecting. Note that the nature of this problem is a little different, because here we are talking about selecting a route or not. In the previous shipment problem, we had talking about the sending number of cars, but here is the nature of problem is a little different. Here we are selecting or not selecting a route. So the decision variables here either could be 0 or 1, that we call a binary decision variables. But for time being, ignore that. We are going to talk more about this type of the decision variables in the integer programming chapter. But distance is time traveling. The time of the traveling is one objective function that we can define. There is another way that we can select our road based on the scoring of the roads. You remember that in the graph we had each road had a different score, different quality, that 3 point or 4 point that for each. So we can define the objective function in a way that we maximize the rating of the roads that we select. But let's work on the just driving hours. So we set up a Excel solver, and the objective function is this one, because we want to minimize the driving time. Let's put the minimization, and then the decision variables are these parameters, and our constraints is net flows that should be equal to so the constraints that supply or demands that we have. And for time being, let's put the decision variables equal to non-negative, and then this type of the simplex that we are choosing the simplex linear programming model and solve this problem. So in this case, we were lucky that all of these numbers are 1 or 0. and and all the constraints are satisfied, and we are getting 11.5 as a number of hours that we want to drive from the station 1 Brigham to the Virginia Beach. So this is this travel time of this. So let's work on the another objective function of this problem, which is the score of this problem. So I create a new Excel sheet, and I want to minimize the maximum. I want to consider the rating. So the objective function cell is this, but here we want to improve. We want to get as much as we could. So the rating score, the average of the rating score should be maximize the scoring that we get. So the type of the objective function is maximize. So let's solve this problem, and you can see still we are lucky that all of these numbers are either 0 or 1, but in some case we may come up with 0.5. that is not true. So we are lucky here that all either numbers are 0 or 1. And then the objective function here for the rating is I got 35, and 15.5 is going to be the time that it's going to take to driving from station 1 to 11. But when I choose the objective function driving time, I had a driving time was smaller. So let's copy this number to the solution that I got in the so these are the two solutions that we got. So in this solution you can see that I got this second solution based on the optimizing the distance, and this I got this solution by optimization of the scoring. You can see this solution is better in terms of the timing, but this solution is better in terms of the scoring. Later in the multi-objective function, multi-objective optimization, you are gonna see that we can have two different functions. We can optimize two different functions and get a different type of solution. And you see, because in terms of the timing, this objective function is better. That means this solution is better, the solution that we had in the previous worksheet. But in terms of the scoring, this function is better. So both of these functions are, we call them non-dominated solution. We are gonna talk more about this kind of functions in the one of the chapters that we are gonna see later.